more students to join. Then we'll start the discussion. Well, let's start our discussion. Before we go for the actual design, let us compare the gears and the belt drives based on their velocity ratio, their maintenance, their peripheral speed and efficiency. Till the time we are expecting more students to join. If we compare a flat belt, this comparison is important from selection point of view or from design consideration. While doing your project, if you are fabricating some machine component, then which machine element you have to pick up, you will decide based on these constraints. Spur gear, helical gear, and worm gear. Worm and worm gear. If we compare with respect to the center distance, for the flat belt, this is used for long center distance. V belt is comparatively shorter as compared to flat belt. Chain drive again comparatively shorter as compared to flat belt. Rope drives, they are used for very long distance. We have seen in case of elevators or for lifting the load in cranes, for very long distance, we go for rope drive. All the gear drives, you know, this is for very short distance. Center distance between two shafts has to be very short. What about velocity ratio? Which one will give you maximum velocity ratio? Aman? Aman, worm. You are right. So velocity ratio in case of flat belt is restricted to 4 to 6, but a maximum of 10 can be achieved, although it won't be very efficient. Here the velocity ratio can go as high as 15 for chain drive. Again, comparable with flat drive. Rope drive, again comparable with flat belt. Spur gear is low, 1 to 6. Helical gear, maybe maximum of 10. For worm wheel, it can go up to 100, 200, 300. But with more and more velocity ratio, the efficiency goes down. If we talk about the maintenance, which one requires minimum maintenance? Which amongst these would require minimum maintenance? Rope drive, spur gear minimum? No. Belt drive, yes. Flat belt drive will require minimum of the maintenance. All other will require medium level maintenance. And maintenance is very high for worm and worm wheel. That is because this produces lot of heat. Peripheral velocity or the speed in meter per second. This is normally in the range of 5 to 30 meter per second. V-belt in the same range. Chain drive around 20 to 25 meter per second. This rope drive again around this range. Spur gear can go up to 35 to 40 meter per second. Around 35 meter per second. If I talk about efficiency, which one would be the most efficient? Most efficient system? Spur gear and helical gear. Here the range would be 92 to 98%. V-belt efficiency is less, 87 to 96%. Rope drive, again good efficiency. Chain drive and rope drive, almost the same. Spur gear, high efficiency, 98%. Helical gear, high efficiency. Worm gear will again have low efficiency. We have seen other day in the calculation, we got the efficiency for the worm wheel as 82%. Cost. If just to establish a relative number, if this is costing 1 or 100 or 1000 rupees, what would the cost for V-belt as compared to this? This would cost 3 rupees. So this would be 3 times of this. Chain belt, all the more higher, would cost 5 rupees. Rope drive with the drum and other accessories would cost around 10 rupees. Spur gear as compared to 1 rupee cost of belt drive would cost around 15 rupees. So this would be as costly as 15 times of V-belt. This is just a general number. We talk about the precision gears and the commercial gears, and then there would be a range. So this might become 10 times. If you go for a very high precision gear, this might go even more than this. Helical gears are always costlier than spur gear. So if this is costing 15 rupees, this would cost 25 rupees. And the worm and the worm wheel would be the costliest of the lot, 35 rupees. This is just to give you a fair idea. This is not exactly 35 times of this. As I said, it entirely depends upon what kind of precision we are talking about. Okay. Well, we have 66 students now. So what is creep? We were discussing about creep the other day. Do you understand me the term creep, Devesh? Devesh, you are there. What is creep? Who is answering me? Deformation due to compression and extension. Yes. So while the pulley is rotating and belt is continuously passing through it, stretching and then again is compressed while it is moving the distance between the two pulleys. This relative motion between the belt and the pulley and stretching and unstretching. So the tension increases and then it decreases and increases and decreases. This stretching and unstretching of belt, this is creep, which will reduce the life of the belt. Also, we were talking about why there's a limitation of velocity ratio, why there's a limitation of center distance. Since we have to design, we must know why we have the limitation. What happens if we go on increasing the value of delta? Sorry for this drawing. Pulley with diameter d1, angle of contact theta 1, pulley with diameter d2, angle of contact theta 2. Why rope is costlier than chain drive? We'll talk about rope, how they are made out of steel wires, and then number of fibers of steel, they are twisted, and a bunch of those twists, they are forming another twist, and then there's a core inside this. So we are coming to rope drive. I'll tell you why it is costly and how the factor of safety here in the rope drive is very high, because this is used for lifting very heavy load in long distance, so the cost is higher than the chain drive. We are going to design wheel belt. Hello, my voice is not clear. I have some internet issues and I'm working on my mobile hotspot. Let me know, is that better now? Okay, good. So the angle of contact on the smaller pulley with diameter d1 and the larger pulley with diameter d2 is given by the expression pi minus difference between the diameters upon center distance, 2 times of this, which is pi minus d2 minus d1 by c. Now if I write down the ratio between the diameters, the larger diameter pulley upon the smaller diameter pulley as m. I'm trying to establish a correlation between the ratio of diameters and the value of theta. And I'm writing this as pi minus d2 minus d1 by d1 is m times d1 by c. Now what would happen if the value of m goes up? If this ratio d2 by d1 goes up, what would happen? If the value of m increases, what happens to theta? This is minus here. So if I increase m, what will happen to theta? Increase or decrease? Yes, please. Theta would decrease. And what will happen to the rated power or the design power if theta goes down? This depends upon e raised to mu theta. So if theta goes down, what about power? this will also decrease. And which means this ratio cannot be increased beyond a limit. And if this ratio cannot be increased beyond limit, there is a limitation to velocity ratio also. That is the reason velocity ratio cannot be very high. Because if you increase this difference between the diameters, the value of angle of contact goes down and the rated power goes down. So if you increase the velocity ratio from 4 to 10, the power transmission capacity goes down. But if the value of D1 increases, this is the driving pulley. If D1 increases, the value of Vp also increases, right? The peripheral velocity also increases, and the power is T1 minus T2 into Vp. So if Vp increases, then what happens with PR, rated power? What if the peripheral velocity increases? Then this increases. And with increase in the diameter D1, if D1 is increased, either you increase M or you increase D, in both the case, this value of theta will go down. With increasing D1 also, theta goes down. So this puts a limit to the diameter D1 also. If you increase the value of D1, Vp is increasing, power transmission capacity is increasing. But with increase in D1, as shown in this formula for the smaller pulley, the value of theta 1 is going down, the rated power goes down. So increase in the diameter, this is having opposing effect. This is another question for interview or question for IES or GATE or technical questions. Such kind of questions will not have a direct answer. What happens with the increase in diameter? So you see, with the increase in diameter, the power increases because of increase in the peripheral velocity, or the power transmission decreases because of decrease in the angle of contact theta. Now, which parameter is dominant, that has to be seen. And so directly with increase in diameter, pressure increases, the power transmission capacity increases. This cannot be commented. So we'll see what is the value of peripheral velocity for which the power transmission is maximum. Our ultimate aim is that the power transmission should be maximum. So we have seen that by formula, the rated power is K minus 1 by K, where what is K? What is K? What is K here? Shravya? In the last class we have discussed
T1 by
this.
T2.
It is T1 by T2 or it is e raised to mu theta?
Yes, ma'am.
This is K here. T1 by T2 is K, which is equal to e raised to mu theta. And so I am rewriting the same expression, this into S naught A Vp minus rho A Vp is the peripheral velocity cube, where rho A V cube, this is a term which comes from the centrifugal tension Tc. So to check for the value of Vp for maximum power transmission, let us differentiate this with respect to Vp. We are differentiating rated power with respect to Vp. Now this term is constant, this term is constant. We will get S naught into A minus 3 times rho A Vp square into this constant, which is equal to 0, or I get P rho Vp square is equal to S naught. Other terms, they are constant, or the condition for maximum power transmission is Vp should be equal to S naught upon 3 times rho. What is S naught? What is S naught? And what is rho? Saurabh? Yes, it is strength of the material. And what is rho? Density of the material. And so this puts the limit on Vp. For the good working speed, Vp should be in the range of 900 to 1200 meter per minute. This is again given in the design data book. Suppose the value of peripheral velocity is not given, you can safely assume a value in this range. So you can safely assume 1000 meter per minute. So when we are designing a belt, we have to select the material of the belt. We have a choice of material given in the data book. We have to assume what is the section of the belt, whether it is rectangular section, whether it is a square section. We have to assume the length, or we have to calculate the length of the belt, and we have to see what is the kind of joint. Flat belt is not seamless, so somewhere there would be a joint. So what is the type of joint that would decide how much is the efficiency. So that is again given in the data book. Similarly, for the pulley, normally it is cast iron pulley, but we have to still pick up a material for the standard cast iron or the standard material chart. Size of the pulley, which is essentially the diameter of the pulley, and then the construction of the pulley. So construction is like we have designed the gear plank. Similarly, for the pulley, it could be a solid pulley, it could be a ribbed pulley, armed pulley, web pulley. So there is a range of design. Area of the belt when we select, it is normally a rectangular cross section. It could be a section like this, or it could be a section like this. This is the section with this as thickness, this as width of the belt, or for the same area we can increase B and we can reduce T. What would be the advantages and limitation of taking two different sections? Whenever the value of T is large, this would be more flexible or less flexible. If we increase the thickness of the belt, the flexibility would increase or decrease. The flexibility goes down. And because it will become rigid, the bending stress due to the wrapping would increase. The tension due to bending or stress due to bending. And this bending is because it is wrapped around the belt, this increases. So we will normally prefer a thinner section like this with a larger width and a thinner section over this kind of section. With all these parameters, what if I go on increasing the width of the belt? What if I take this kind of thickness? Very small thickness, very large width. Would this be better over this one? What do you say? If reducing the thickness is increasing the flexibility, it is decreasing the bending stress. Yeah, strength is not decreasing, but because the width of the belt is increasing, the width of the pulley would also increase. Width of pulley would also increase, and the pulley will become very large, very bulky. If the weight of the pulley is increasing, width of the pulley increases, weight of the pulley increases. The centrifugal force will also increase, and this will increase the overall cost. And so out of these three, the medium section would be always preferred. Do you know what is crowning of belt? What is crowning of pulley, not belt? Do you know what is crowning? Anybody? Daitva? Fixing the belt over the pulley? Not exactly. Instead of having a flat pulley like this, small projection is given. Yes, a hump is given on the pulley. This is known as crowning. Now, can you tell me what is the reason for this crowning of pulley? What is the advantage? Oh, yes, it avoids slipping. It prevents slipping. How? How does this prevent slipping? The belt is somewhere here. Now with the crowning, the radius of the pulley here is larger as compared to this radius. This radius is R1. This is the radius at the center, which is larger than the radius at the ends. Now as the radius increases, the centrifugal force would increase. And with the increase in the centrifugal force, if the belt is trying to slip away here because the centrifugal force is more here, this will try to align the belt. So if the belt is moving here because of the centrifugal force, it will tend to come back at the center. Similarly, if it is trying to move here, the centrifugal force will try to bring it back. So this crowning of pulley, this helps in self-aligning of the belt. And it avoids slipping. So the belt will have a tendency to come back to this region, the central region. And if we select the diameter of the pulley as D is say the pulley diameter, thickness of the belt is normally taken as 0.2 times of smaller diameter to 0.03 times smaller diameter. We have a concept of initial tension in the belt, which we'll discuss again later. Let us start solving a numerical first. So look at the problem definition. It could be as small as 10 kilowatt power is to be transmitted. 10 kilowatt power is to be transmitted from a 1440 RPM motor to a 400 RPM line shaft design the belt drive. Smaller the problem statement, more difficult it is to design. Why? Why so? Why do you think it would be difficult to design? Yes, because minimum data is given and you have to assume a lot of data and you have to check for whatever you are assuming. More assumptions, yes. Okay, let's start with the design. Open the design data book. Belt drives is page number 155, chapter 15. Table 15.1. You start with the design power. Rated power is 10 kilowatt. So what is the design power? Rated power into service factor K1 into the inclination factor K theta. What is inclination factor? If your two pulleys are placed like this and if your belt is moving in this particular fashion, this is the theta. So anything other than horizontal and this theta will come into role, will come into picture. So if the angle with horizontal is 0, then k theta term is 1. So if nothing is given, we'll assume this theta is 0. K theta is 1. Since we have to assume everything, you can assume theta is 30 degrees, but why to unnecessarily complicate the problem, right? So let us try to keep it simple. Then for the service factor, refer table given for driving machinery is electric motor, driven machinery is a line shaft. A line shaft is a shaft for large power transmission, usually in industrial applications. This is known as line shaft. So for driving machinery as electric motor driven as line shaft, what is the value of K1? What is K1? 1.1. Is it 1.15 or 1.1? Which makes it 11 kilowatt. Next is we have to select the material. There are different materials given. For belt material, refer table 15.5. For belt material. Table 15.5. You have a leather material, then rubber and cotton. So most commonly used is leather. Then it is for light duty, medium duty and heavy duty. You have oak tanned leather, then here is a chrome tanned leather belt. So this chrome tanned leather belt. So it's a leather belt with a layer of chrome over it, and this is for the medium duty, and this is the most optimum or the most preferred choice. So again, if nothing is mentioned, then we normally go with this chrome tanned leather belt. CTLB, chrome tanned leather belt. So we are selecting this for the chrome tanned leather belt. What is the value of S naught? The value is normally 3 megapascal. Where is that mentioned? 2.8 to 3.8 is the allowable stress. So we have to select some value in this range. Ultimate strength is 2.8 to 3.8 megapascal. Let us pick up some value. Should we go with 3.5 MPa? You can pick up any value. You can use 3, you can use 3.2. Let us not be, say, 3.5. Then we have to select the joint. As I told, this belt is not seamless. So it comes in a long length and then it has to be joined somewhere. So now this, the same page, table 15.6, you can see it is cemented by the manufacturer, cemented at the side, wire laced by machine, by hand. So there are so many options given there, and that will define what is the efficiency of the joint, how easily it would fail or can sustain the load. So let us assume we are taking a wire laced by machine type of joint. Again, I'm repeating, you are free to choose. Say the type of joint is cemented at the site with efficiency 98%. So whatever you are assuming, you have to mention. Like here we have assumed CTLB. Again, let us assume the joint is wire laced by machine. Wire laced is a kind of stapling, like you are stapling two ends of paper or a cloth. Likewise, this is connected with the help of a thin wire lacing by machine. So what is the efficiency? Wire laced by machine. This is the efficiency of the joint, 90%. And so the strength becomes 0.9 times 3.5. What is this? How much? Value of S naught? 3.15. Correct. Next, density for chrome tan leather belt, density is given as 0.97. Multiply it with 1000 to get it in kg per millimeter cube. Then we have to take up a peripheral velocity. What is the peripheral velocity that we'll select? I gave you the range. The next page, table for selecting the peripheral velocity, table 15.4, is giving you for maximum power and economy, the range is 1500 to 1800. And for the longer belt life, the range is 900 to 1200. So we have to decide whether we want to go with maximum power and economy or for longer belt life. Say I want longer belt life. If you want for economy and maximum power, you can go with that. For longer belt life, I am assuming this in the range of 900 to 1200. Let me take it as 1000 meter per minute, which makes the calculation easy. Why do we need to assume this peripheral velocity is, since nothing is given, this peripheral velocity will now give me at least a diameter of one pulley. N1 I know, this is 1440 RPM motor. If I am assuming this peripheral velocity, I get the value of T1, the diameter of the smaller pulley. Give me what is the diameter of the smaller pulley from this formula. And this is meter per minute. This 60 is not required. Give me the diameter of the smaller pulley. Yes, 220 millimeters. N1 by N2 is known. 1440 to 400. So you also know what is the diameter of the larger pulley. We are assuming there is no slip, there is no creep, and there is no loss. That is again an assumption. Assuming no slip. Ideally, you should assume 2% slip. And if you are assuming no slip, then you must mention. Give me the diameter of the larger pulley. You want to go with slip, without slip? $795 with no slip. Do you want to consider 2% slip? If you want to go with, say, 2% slip, what would be? Okay, let us consider a slip. 1 minus this percentage slip N1 D1. This is equal to N2 D2. Give me D2 now. Slip is normally 1.5 to 2%. So we are assuming 2% slip. What is D2 with slip of 2%? 780. Bharti is saying 780. Somebody is giving me answer 630. Yeah, 780 is correct. With 2% slip, this becomes 780 mm. Then we have to consider the center distance, C. The maximum center distance, as per the data book says, it cannot exceed 7.5 meters. And the minimum center distance, this has to be 3.5 times the larger pulley diameter. So we go with this and see that this is not exceeding 7.5 meters. So if there is no space constraint, instead of going with this minimum value, you can safely go with 4 times D2. This is minimum. So you can go with 4 times of the larger pulley diameter, 4.5 times larger pulley diameter, as long as this is not exceeding 7.5 meters. So assuming the center distance as 4 times of larger pulley diameter, what is the center distance? Center distance is coming out to be 3120 millimeters. 3 meters, right? 3 meters. Next, mu. Coefficient of friction. What is the material for belt? Leather. What is usually the material for the pulley? Unless specified, we'll go with cast iron pulley. Wood pulley or paper pulley is again rarely used for limited application. So we are assuming pulley made out of cast iron. With what is the value of mu? Same page. Leather belt, cast iron pulley. This is 0.35. What next? We have to find the value of theta, so that we get the ratio of belt tension. So theta for the smaller pulley, you know, is pi minus d2 minus d1 by c. You will get it in radians, convert it into degree, or give me the answer in radians. Both the diameters you know, center distance you know, give me the value of theta. Is that coming out to be 2.9? Theta is 2.9 radians. Okay, 2.96. Now you know mu, you know theta, so you can easily find out what is the ratio of belt tensions T1 by T2, which is equal to e raised to mu theta. And you also know that T1 minus T2 into the peripheral velocity, this is equal to the design power. Design power we know, Vp we have assumed. So from these two equations, you will get what is the tight side tension and what is the slack side tension. Yeah, come on, do it quickly.
Ma'am, for theta, should we consider it as radians only?
Radians, yes. For this calculation, it has to be in radians. So it is coming out to be T2 is 6 newtons, T1 is 17. Yeah, others please confirm value of T1 and T2. Saurabh, Devesh, Tanvi, give me the values for T1 and T2. Ujjwal, you are there? Ujjwal, on number 120.
Yes, ma'am.
Ujjwal, give me the answers.
Yes, ma'am.
Prathamesh,
Yes, ma'am.
T2 is 363. Jewel is giving 363 as T2. And what is T1? Yeah, 1023 and 363. This is matching with my values as well. Yeah, others, please confirm your values. Manas is also giving same. Yeah, so we'll go with this 1000 newtons tight side tension, 362 or 63 newtons slack side tension. Plus D2 by 2. Give me what is the space required, and then we have to find out the area of the belt. And as I told you, for flat belt, normally the bending tension is not considered. Centrifugal tension is considered, and this should be equal to A into S naught. T1 we know. TC we have to find out. This is rho A into V square, which is A into S naught. Or area of the belt, this comes out to be T1 upon S naught minus rho V square. So 3620 is the space required, right? Okay. So when it's a design a belt, you have to decide what all data you have to provide. So essentially you have to provide the belt tensions, you have to provide the center distance, you have to provide the space required, then you have to give the belt section. For belt section, we have to find out what is the cross section of the belt first. T1 you know, S naught you know, density you know, velocity you know. Give me the value of area in millimeter square. Area is how much? 355 mm square. Manas, Prathamesh, please confirm. Rushika, what is your value?
Ma'am, I'm yet to calculate. I'm calculating.
Utkarsh, you are there?
Yes, ma'am.
Okay. Manas is also giving me 355. This looks good. 355 mm square. How do you get the cross section now? Area is B into T, which is 355. Thickness of the belt is normally taken as 0.02 times the diameter to 0.03 times the diameter. So if I assume the thickness, this is again given in the data book, 0.02 is normal and 0.03 is the maximum. Should I take a range in between this, 0.025 times D1? You can go with 0.02 as well. We have a check later on, what should be the maximum belt width. So we'll check whatever we have assumed. Give me what is the thickness that comes out from this. Give me what is the width that comes out from this. And we also have the formula for the maximum belt width. Again given in the design data book, table 15.4, 1.33 times this diameter of the smaller pulley. This is the maximum width of the belt. This cannot cross this. So what is thickness, Sushmita? T is 19. Thickness is 19 mm. Sufficiently large. 18. What is B and what is T? Our area is 355. Your T is coming out to be 19. B is 18. Almost a square section. We want B value to be larger than T value. T is 5.5. This is correct. With T as 5.5, what is B? B is 64.2. Please check this. This must be less than B max. What is 1.33 times diameter of the smaller pulley? B maximum is 293. So this is safe. So our B value is definitely less than B maximum. It is not crossing the maximum limit. So from this perspective, this design is safe. We have to also check for the initial tension. There is a range of initial tension given there. So this part we'll take up in the next class. We have to derive the initial tension. We have to find out how this initial tension depends upon the other two factors. So as of now, we'll quickly revise whatever we have discussed or how we have solved this problem today, and then we'll stop. Give me just a minute. I know you don't have a class after this. So these are some of the basic terminologies of how the diameter changes or the change in the angle of contact affects the power transmission capacity. And we have also seen for the maximum power to be transferred, the peripheral velocity should be given by under root of S naught by 3 rho. So design of belt involves a selection of material of the belt, section of the belt, that is B by T, length of the belt. This we have to still calculate what is the length of the belt, type of the joint. We have to also design pulley. So we have to select the material which we have done, size of the pulley, which is the diameter and the width, and the construction of the pulley. So this part we are yet to do. Area should be selected such that B is always greater than T and it is flexible enough, but you cannot increase B beyond a limit because then the size of the pulley would increase. To avoid slip, rounding is done on the pulley, which ensures that the belt is aligning by itself. Well, a quick look on this problem where 10 kilowatt power is to be transmitted between 40 RPM motor to a 400 RPM line shaft. We have to design a belt drive. We refer the design data book. And from the design data book, we find out what is the design power. Design power is rated power into the service factor. Theta, we are assuming it to be horizontal, and so K theta is taken as 1. You are free to pick up if it is specified in the problem what is the value of theta. So this design power comes out to be 11 kilowatt. We have to assume the material. We have taken the leather belt, which is a chrome tanned leather belt, the most popular belt which is used in industrial application. The value of S0 is given in this range. You are free to select any value in between this. We are assuming the joint is wire laced by a machine with efficiency 90%, and so S0 value becomes 3.15. Density for this material is given. We are assuming the peripheral velocity for longer belt life as 1000 meter per minute. From this, since N1 is known, we find out what are the diameter of the pulley with slip, without slip. Whatever you are assuming, with no slip, this is a diameter, with 2% slip, this is a diameter. If you are assuming 1.5% slip, you have to give that diameter and continue with your problem. Maximum center distance should not exceed 7.5 meters. Minimum is 3.5 times the diameter of the larger pulley. You can go with 4 times or you can go with 4.5 times. Make sure this doesn't exceed 7.5 meters. You increase the center distance, the length of the belt increases, the cost of the belt will increase. And so you cannot go with a value as high as 7.5 meters. So we have chosen a value of 3.1 meters for the given material, cast iron pulley and leather belt. Value of mu is given as 0.35. With both the diameters and center distance known, we can find out what is the angle of overlap theta. With mu and theta known, with Vp and Pd known, now we can find out what are the belt tensions T1 and T2. Space is considered in this fashion. Now we have to find out the area of the belt or the cross section of the belt. So we know that T1 plus Tc is equal to A times S0. Tc is the centrifugal tension, rho Av square. And from here we get what the area is, 355 mm square. This area is the rectangular cross-section area B by T. The value of T is limited to 0.02 times D to 0.03 times D. With our value in this range, we got the value of thickness as 5.5 mm and width of the belt as 64 mm, which is less than B max. So this is the cross-section of the belt that we have taken, 5.5 by 64 mm width. CT BP. Chrome tanned leather belt. We'll design the pulley and the remaining factors in the next class. Yeah, you're free to ask questions if any. Any questions or we stop here? No questions? Manas? Prathamesh? No, okay, good. So we'll stop here. Thank you so much.